Unit 7A will cover real fluids and viscosity. Unit 6A and 6B dealt with ideal fluids, which meant that we ignored a lot of the features that make fluids realistic. One such feature is viscosity, which is the resistance to flow that a fluid feels due to friction within the fluid itself. So some fluids flow easier than others. For example, it's very hard to get maple syrup or honey flowing, but water flows pretty easily, and this is related to the viscosity of the fluid. Maple syrup and honey have a high viscosity, whereas water has a low viscosity. Before we talk more about viscosity, we should mention that there are two ways in which fluids can flow. They either have laminar flow, where they flow in smooth, connected layers that aren't broken up at all, or turbulent flow, where mixtures of the fluid end up changing its flow so that it's more chaotic and not smooth and in a streamline. For example, the smoke at the bottom of this image here, you see that the fluid is moving as a smooth connected layer. That's like laminar flow. But near the top, the fluid starts to get mixed up and starts flowing multiple ways at the same time, and that characterizes turbulent flow. In fluids, we can think about one small chunk of volume and how it flows through a system. We like to think about these as streamlines. When there's laminar flow, the streamlines are smooth and consistent. Only one layer rubs up against a layer below or above it. But with turbulent flow, the streamlines are not always to the same direction, and they mix and make these vortices and swirls. There are two main things that cause turbulence in a fluid. Either obstructions or objects blocking their path, or extremely high speeds will lead to more turbulent flow as well. But we'll talk more about that in the next unit. So now let's talk more about viscosity. Viscosity is a quantity that we can actually measure, and it has units of poise, which is 1 Pascal times a second. We use the Greek letter eta to denote the viscosity in math form. And one way to measure the viscosity is with this two-plate system where we put a liquid between two plates. We keep one fixed at the bottom at 0 speed, and then we move the other one on the top at a constant speed so that we can measure the amount of force that is felt by these layers dragging on one another. Therefore, we can use this equation to calculate the viscosity and figure out what units are inside of viscosity. Eta is the coefficient of viscosity, and you can see several different viscosities given for some common fluids. And then the other measurements from this experiment are also shown on the right side with force, length, velocity, and area. A fluid's viscosity is related to its resistance to flowing. Pressure differences are what cause a fluid to flow. Fluids will always flow from high pressure to low pressure, and therefore we can characterize a flow rate associated with this pressure difference. The flow rate will depend on the pressure difference between 1 and 2 points of the system and the resistance in the system, which is related to the viscosity. We can calculate the resistance in a fluid system by using Poiseuille's law. And we can use this equation here to calculate the total resistance for some system that has a length L and a radius R. Plugging this resistance formula into the one from the last slide gives you an equation that can be used to calculate the flow rate based on characteristics of your system and a pressure difference that is applied. You can use a laminar flow diagram to represent how different layers of fluid are moving throughout a system. We see that there's this velocity profile that depicts the middle layer as being the fastest moving, and then the other ones moving slower due to friction between either the walls of the container or neighboring layers. Unit 7A is a short week and a short unit, so be ready to encounter these topics again in Unit 7B. I'll see you in the next one.